In digital communications, we will discuss cyclic codes in this chapter. So what is cyclic code? Earlier we have been discussed linear block codes in channel coding. So this is another coding, cyclic code. So in the channel coding, there are different codes, linear block code, cyclic code, convolutional code. Here we will discuss cyclic code. And the properties of the cyclic code is, one is linear property, other one is cyclic property. So linear property is sum of any two code words is also a code word. So that is linear. And cyclic property, so cyclic shift of any code word is also a code word. So the cyclic code which exhibits the fundamental property of linearity and the cyclic property. So n-bit code word, we generate n-bit code word from the k message bits. So this is what n-tuple code word. See, this is code word C, C0, C1, C2, Cn minus 1. This is a n-bit code word, n-bit code word, and see the code word is cyclic shift, cyclic shift. This is what cyclic shift. This is also a code word. This is again cyclic shift of. This is also code word. So either right shift or left shift, that gives a code word. So that is the cyclic property. And we define the code word in the polynomial. That is the code polynomial C of x. Here, that code word C is represented with the polynomial of x, that every multiplication of the x is right shift, one shift of the code word. Okay. So C0 plus C1x plus C1x square, C2 x square, and etc. Cn minus 1 x power n minus 1. So these are the code polynomial. So every x represents one bit shift power of x. So this is a code polynomial representation. The code polynomial is in the form of a product of two polynomials. One is generator polynomial, out of which g of x. So here a of x, the polynomial is having k minus the order, and g of x, that is generator polynomial, we can say it n minus kth order. So the code word is generated the combination of the message bits and the parity bits. So for the k bit message, this is what we want to generate, n minus n comma k code word, n comma k code word, the k bit message word, and n minus k parity bits are added. And to generate this cyclic code, so you see the m of x, the polynomial, the m of x, which is message bit polynomial. This is called k bit message polynomial, represented m0, m1x plus m2x square, etc. mk minus 1 x power k minus 1. Similarly, parity bit polynomial b of x, we represent b0 plus b1 of x, b1x plus b2x square, etc. bn n minus k minus 1 x power n minus k minus 1, n minus kth order. So these parity bits are added to the message bit code word, message bit block. So these we can add parity bits either side. So have added left side. So here the generator polynomial is n minus kth order. So if nth order polynomial x power n plus 1 is represented, the factors of this nth order polynomial is one of the g of x, n minus kth order. So that n minus kth order g of x can be represented generator polynomial n minus kth order 1 plus sigma g I x power I 1 I equal to 1 to n minus k minus 1. So this is plus x power n minus k. So this is what the n minus k the coefficients g, the n minus k minus 1 coefficients g of I will be, the coefficients will be connected. So this is represented generator polynomial. And to generate this cyclic code systematically, where the message bits are k bit message and n minus k parity bits, we need systematically the code word by shifting the message word of n minus k. So the message bits are shifted right. So that is m of x multiplied with x power n minus k. Okay, this is shifted to the right side, and we add parity bit here, the parity polynomial here. This is what we get the code polynomial. So to generate this code polynomial as b of x plus m of x x power n minus k. So how do you get this code word? As we mentioned, the product of two polynomials ax, gx. So this is made equal. So here in this entire equation, we divide with the generator polynomial g of x. So what happens here? By dividing a of x equal to b of x divided by g of x plus m of x x power n minus k, okay, divided by g of x. Okay. So now this is where we add modular addition for left side and right side by b of x by g of x. Okay, b of x by g of x. So we add here a of x plus b of x divided by g of x. So b of x by g of x plus b of x by g of x becomes 0 in the modular additions. So this becomes m of x power n minus k divided by g of x. So this is what the ultimate thing, where m of x multiplied with x power n minus k, which is being shifted right, by dividing with the generator polynomial, we get the remainder. This is the coefficient and this is remainder. B of x is the remainder. This is what remainder. If you find this remainder, you can just add remainder to the product of m of x and the x power n minus k. So these are the steps. Just multiply m of x into x power n minus k and divide with the generator polynomial g of x. Obtain the remainder b of x. Add b of x to the product. This product, we will get the code word. We see the example here for the message 1011 of 7, 4 for n, k. This is n, k bit 7, 4 cyclic code, 7-bit code word, 4-bit message, and here the m of x, the x power 7, the nth polynomial, we can take the factors 1 plus x into 1 minus 1 plus x cube, and these are the factors x square plus x cube. Okay, so g of x is the order of n minus k. G of x is the order of n minus k. So that is the third order, either this or this g of x. So this is where you choose generator polynomial. I have chosen here, you can choose any polynomial of this third order. So I have chosen 1 plus x cube. Okay. So if we write the message polynomial here 1011, so from the right left side, this is 1 and this is x. and this is x square, this is x cube. So 1 plus x square plus x cube. And we need m of x into x power n minus k. Okay, n minus k. So that is m of x into x cube. You multiply with x cube here. So that becomes x power 6, x power 5, x power 3. And we divide with the generator polynomial. Here we divide with the generator polynomial m of x, x power n minus k divided by g of x. We divide, get the remainder. Now dividing this is generator polynomial. This is what g of x. Okay, this is what g of x. We are dividing, see this x power 6, this is x cube. This x cube times this is x power 6 and x power 4 and x power 3 x cube. Okay, so in the modular addition, this gets cancelled, and this gets cancelled in the modular addition. Okay, x power 5 plus x power 4. This is what. So now then x square times plus x square times x power 5, x power 3, x power square. So this is multiplied, and this is also gets cancelled by modular addition. X power 4 plus x power 3 plus x power 2. Now again x times you multiply x power 4, x square plus x. Again this x power 4 gets cancelled by adding, and x power 3, this x square and x square gets cancelled, and x power 3 plus x. Now one time this is 1 multiplied, so x cube plus x plus 1. So this also gets cancelled, and this is also gets cancelled. We get the remainder b of x equal to 1. Now we add b of x as 1, so that is 1 0 0. 1 0 0 of n minus k ith order 3 bit. Okay, 3 bit. Now this already b of x added plus product with m of x into x power 3. This is what x power n minus k, which is nothing but is x power this product. So 1 plus x cube plus x5 x power 6. 1 plus x cube plus x power 5 x power 6. So this message polynomial is right side, and the parity polynomial is the left side. So this is what 1 0 0 is the parity p, and this is what message. So 1 0 1 1. This is the code word in the cyclic code. We get n bit code word here, 7, 4 cyclic code. So here the parity bits are 1 0 0. This is one of the code in the 4-bit message word. Now, as we said that generator polynomial is the order of n minus k in the product of the product polynomials of the nth order polynomial x power n plus 1. This is like ax into g of x, and g of x, this is taken as parity check polynomial. Whenever this generator polynomial is n minus kth order, the automatically obviously h of x parity check polynomial becomes the kth order. Okay, to verify this, we need to verify by the condition GH transpose is 0. So this is the relation. And now see how to generate this generator polynomial. This is the polynomial n minus kth order. 1 plus gi sigma of gi x power I equal to 1 to n minus k minus 1 x power n minus k. Obviously, parity check polynomial of kth order. This is plus x power k. So these are the coefficients I equal to 1 to k minus 1. We can write it. So if you take the general generator polynomial, that is the encoder. This is what generator polynomial encoder of n minus k stages with feedback shift registers, linear feedback shift registers. These are the shift registers flip-flops we have taken. So these are the flip-flops n minus kth order. So 1 to this is connected 1 plus 1 to n minus k minus 1 with their coefficients of gi, g1, g2, g3, gn minus k minus 1 is the coefficients connected here. These are the modular additions, and this is x power n minus k. These are the shifts from left to right for x power n minus k shifts, and this is being generated with the generator polynomial. So by generator polynomial, by this encoder, we can generate the parity bits in this flip-flops in the shift register. So here the message bits are given at this modular addition, and this is connected here by closing the gate and operated for every shift. And these are the coefficients, the generator polynomial. This encoder is generating the parity bits B0, B1, B2 of n minus kth order. Okay, that parity bits can be taken out at the end. At that, while message bits are given to the encoder, at the same time the message bits are also taken out. So that is shifted right. Later, parity bits can be taken out. So this is the example of encoder in the similar way of previous example of 7, 4. As we said that g of x and h of x is the product polynomial, and we have chosen g of x as 1 plus x cube as before. We can choose either this or this. So we have chosen earlier this, and remaining the product of kth order is the h of x, 1 plus x into 1 plus x square plus x cube becomes h of x. So these are the parity bits. That generator polynomial, the generator encoder, cyclic encoder, generalized encoder is converted into this n minus k 3-bit encoder, like a 3-bit encoder. So this is B0, B1, B2, and this becomes G1 because here, see, this is where 1 plus G1 x plus G2 x. So 1 plus G1 x plus G2 x square plus x cube. So this is what, so this is 0, G1. So this is G1 and this is 1, and G2 is 0 here. No connection. So this is the encoder. So message bits are given here and connected, and every shift at the end, that is B0, B1, B2 are generated, and these parity bits taken out at the end. Now we can generate the parity bits here using encoder. Earlier we generated parity bits as the remainder of the m of x power n minus k product by dividing with a generator polynomial. Here, using encoder, cyclic encoder, we are generating the code word by generating the parity bits in this encoder. See, in this encoder, as generator polynomial 1 plus g of x, in the previous case 1 plus x cube, this is the encoder. Now, what is the message bits here given to the modular addition adder here, and this B2 is also adding here, and this gate is closed. So then this becomes what B0 becomes this B2 of this flip-flop and the message bit is added here. So now generating B0, that is what the present state. Now what is the B0 now? The reset value of B0, B1, B2 taken as B dash, B0 dash, B1 dash, B2 dash. Now this B0 is the present state. So this message M, this message M is added, M plus, these are the modular additions, B2 dash, previous state. This is the message plus B2 dash is given to the B dash. So this is B dash. And B1, this plus this added. So B0 dash, that is the previous state, and this one is added to B1. So B1 equal to B0 dash plus this one is M plus B2 dash, that is this one, M plus B2 dash. So this M plus B2 dash added to the B0 dash, which becomes B1 in the second shift. In third shift again, that is going to B1 is going to directly B2. So the previous state of B1 is connecting to the B2 present. So B1 dash, this is the previous state, becomes B2. Now for the message bit 1011, so I am generating here. So from the LSB, this is what LSB. Okay, this first we are giving 1, and next we are giving 1, and next we are giving 0, next we are giving 1. At the same time we are taken out, and that is being shifted to the right. So this LSB 1, 1, 1, 0, 1 is given, and these are the reset values B0, B1, B2. So this is the message bit taken. So now find the B0 present state, M plus B2 dash. B2 dash is the previous state of this, and M is this. This is M. So this 1 plus 0 becomes, okay, this 1, B dash. 1 plus 0 is 1. Okay, B1 is this plus this, and B0 dash, this one. This means B0 dash, B2 dash, and M. So this and this is the 1. So 1 plus 0 plus 0, 1. Now B2 is B1 dash. B2 is B1 dash. B1 dash is this. So that is being shifted to here. Now in the second bit, next one is taken here. 1 is given here. 1 is given here. Now 1 plus M plus B2 dash, this is 1 plus 0, 1. And B1 is 1 plus B dash, B0 dash, B2 dash, that is 1 plus 1 plus 0. 1 plus 1 is 0, 0 plus 0, 0. And B2 is B1 dash. This is being shifted to 1. So that is where. Now next bit is 0. So this 0 plus 1 is 1. 0 plus 1 plus 1, 0. And this is shifted to here. And next fourth bit is 1. So 1 plus 0, M plus B2 dash, 1 plus 0, 1. And 1 plus B0 dash, B2 dash, 1 plus 1 plus 0, 0. Okay, this 0 is shifted this. So ultimately after 4 shifts, the B0, 1, B1, 0, B2, 0 is getting the parity bits. So then after shifting these 4 bits, message bits to the out, and next this B2 is taken out, and B1 is taken out, and B0 is taken out. That is the code word. So this B100, 1011 is the code word. So we can generate the code word using generator polynomial through encoder. Thank you.